Presentations there, very interesting. I found a lot to contemplate there, actually. I'm going to talk about a little bit about training and test data today, and really how that fits into the trusted AI systems. So a quick recap of AI systems as a whole, a quick introduction to what we mean by the training, and then just talking through the data and why it's important and some of the key issues that we get with data. So there's three main pillars to an AI system. We have the system and the hardware, and that system and hardware is both from a training perspective as well as a inference perspective. So both where you're going to do the training and where you're going to do the deployment. We have the framework and the network that is going to do the training and is going to do the inferencing. So running the algorithms, things like PyTorch or TensorFlow for the framework, things like ResNet, PoseNet for the network. And of course, feeding that framework and that system is the data, and that's training data that we use to teach the AI system, and as well as the data that's going to go in during deployment, which is going to be used for inferencing. And a lot of interesting points already made today about how that data could be used for attacks on the system. So just obviously the audience here probably mostly aware of this. Today I'm going to talk mostly about visual data and visual training data, but the concepts apply equally to other areas such as audio or textual kind of data. And just so we're all on the same sort of phrase, the same sort of frame, training basically consists of giving a machine or giving the system a lot of pairs of data and annotation. In our case, visual data. So the example here, teaching a system what a banana is. So we give it lots of images of bananas. And in this case, the annotation is very simple, just a banana. We give it lots of pictures of what is not a banana. So cars, tigers in this example. We go through this and we train it, and we look at it, we predict the output, we measure the error, and we update it. We then go on to the test sequences. And in this example, you can see we correctly surmise the banana and the tricycle and the zucchini or courgette. Obviously you can see why it thinks that that's a banana. It's predicting it as a banana, but it's obviously zucchini. So this has showed us there is a weakness there in our network and in our system that we need to address. So in terms of this data gathering, we have to think very carefully about what is the target application, and the target application will very much depend on what accuracy we're trying to achieve. If we're trying to, going back to the previous examples of automotive, if we're trying to detect a child there or any pedestrian, in fact, it's critical that we identify them very accurately. We want the car to brake. We don't want the car to hit a pedestrian. On the other hand, if we're counting the number of people going into a shopping centre to check that the capacity of the building is there, we probably have a reasonable margin for error in that. So it's very important to understand the target application in order to understand the accuracy and the types of data that we want. So where do we get this data from? Well, we can go out and get real world data, and there's a lot of existing databases out there. So you might have come across things like ImageNet and CocoNet and Coco. There's lots of things out there. First of all, a lot of them are not allowed for commercial implications. But the bigger point really is that the content there is unknown. You have thousands or tens of thousands of images, and you have no idea what that content is. So if you're trying to build a system that you can trust and understand, if you have not obtained that data yourself, you haven't specified it and obtained it, that whole chain of trust is broken. We can't rely on the results from the network that based on that kind of data. And data provenance really is critical. And we're seeing increasingly legal cases where people are being asked to go back and prove what data was used to teach your AI system. What is that black box that you've created? And obviously there's famous cases with where systems can be racist or sexist, or cars can have crashes and things like that, and people are being asked to go back and prove what they've done. So that data provenance is critical, and taking off-the-shelf data sets is not going to necessarily allow you to understand that. And even in the case of pre-trained networks, it's even worse, because you have a network that has been trained on some data, you don't even have access to that data. On the right-hand side, we can see there in the diagram, we do need a huge amount of data. We've got to have the training data. We've got to have validation data to test against that training data, and then the test data to test the model. That's not the end of it. Once we're deployed in the real world, we're going to come up with more data that we're putting in, and we need to constantly go back and review that deployed model. So there's a huge number of issues. I'll go into a few of these in a little bit more detail as we're gathering the data for a trusted AI system. We're going to have very large data sets, and this has already been touched on a couple of times about where do we store these large data sets to ensure the security? Where do we obtain the large data sets from? GDPR is a massive issue. Using people's faces and visual imagery for training data sets is a lot of problems around that, if you're trying to use people's images without their explicit consent to use them for that purpose. I've mentioned already we need annotations in order to train the system, and making sure that those annotations are accurate, vital. One of the things that's often overlooked is that as I obtain data, that data is perhaps going to be obtained from a camera system that I've set up and recorded. If that camera system is not the same as the camera that's used actually in deployment in the field, actually there's a real mismatch there between the data that you're using and the data for the system that's deployed. And that's a real problem, giving you inaccuracies in the systems there. And another couple of things at the bottom there, getting that hold of that corner case data can be very difficult. It's not easy to record. Getting the appropriate environmental conditions. If I'm sat in my office here in Kings Langley, we very, very rarely get snow here. It happens very occasionally. But if I want to try to understand modeling, what's happening to our car park in the snow, how is the parking space allocation, what's happening there, it's very difficult to get that data in the real world, to have to wait for that. As I mentioned, the traditional way to get real world data is to get real world data. So that either involves scouring the web. Now that's very, very fraught with issues around the rights to it and whether you can do it or not, or you end up setting up your own systems for recording. This obviously has a lot of advantages. If you're doing this, you're recording your own data, you own the data, you understand exactly what you've recorded, but it is expensive, and that's only half the picture, because then you need to go and annotate all of that data, which is a very slow, costly job. And as I've mentioned already, you have to be very sure that you're going to get an accurate set of annotations, otherwise that chain of trust is lost. Once we have our data set, we're often going to need to add to that. So from our base annotation, from our base data set, we're going to augment that. And there's a number of reasons for this, but basically it comes down to trying to cover as many cases as we can that are going to occur in the real world. Some examples that are here, so the condensation on a camera lens, use of older security cameras, things like interference on the images, the lens distortion that I've already mentioned, so modeling that real world implementation needs to be distorted to match what you're going to actually be using in the deployment system. And so the way that we do that is we take the image that we've captured and apply a number of transformations to that. So cropping, mirroring, distorting, saturation, and so on. Now, this does give us a much larger data set, much more chance that we will have something which is matching the what we're trying to achieve in the real world. Now, what is important here is that obviously, so long as we have some trusted imagery to start with, and we understand the transformations applying, then this is going to still enable us to maintain that chain of trust that we have in there, because we're starting out with something. Obviously, as you move through distortions, you can move further and further away from that trusted data set that you have. In order to train the AI system to do what you want, you need very precise annotations. If we're looking at something on the left-hand side here, a very simple bounding box, labeled as a man, it's fairly straightforward to do that with data, and I can send out real world data and I can get that, and I can be reasonably sure that that's going to be accurate. Although even there, errors are possible, because, if I'm looking at the back here, I've made a judgment that from the back of that person, as the person sitting annotating, I've perhaps made a judgment that I think that that is a man. It could be a woman. The perspective of the image, again, do I know what age that person is? What sex that person is? No, not really. So there is, even at this point, judgment being made within your annotations. And as we move through these levels of complexity of annotations, it gets harder and harder for humans to accurately give those annotations. And at each of these, again, there's a level of accuracy that depends on your final destination as to what level of accuracy you really need. So potentially, in the first examples that I gave for a car, self-driving vehicle, you want your semantic segmentation to be very accurate. For counting people going into a supermarket, it may be less of a requirement. And one of the key things that we see within the AI systems that is really important is this concept of data drift. And I've given a couple of common examples here of the way that we see data changing over time. So just after you've deployed an AI system, you can't leave it and assume that it's going to be okay for the rest of time. The top example here, obviously, we were used at one point to sort of very, very crowded underground trains, lots of people on. We moved through to sort of the concept of a little bit of social distancing there in the middle, keeping a little bit of space between people. The third one there, obviously, we've moved on to the concept of having to wear face masks and that sort of thing. So if we're trying to do some analysis of, is our transport system, overcrowded, or if we're looking at a security system on the transport system, that data drift has to be addressed. Likewise, the lower one, if we're looking at home deliveries and we want to understand, Is our home safe and secure? What's the difference between a delivery person and a burglar? We've moved from some of the traditional deliveries which came to the house every day in the form of a milk float and a milkman, moving on to the sort of Amazon or brown box packages we're getting today. Looking at the future, we may well see things like drone deliveries happening or last mile robots. And so these things here need to be addressed in your data set. You need to constantly update that data set to have the trust within it. And one of the other things to ensure that we've got a trusted AI system and that we can trust that is looking at that bias level. And, obviously sometimes we have intentional bias, but we want to avoid any unintentional bias. And so by having the right diversity in the data set is really important. So things like having positional diversity, location diversity, color and shape, human diversity is absolutely critical. And indeed, sometimes it will actually break your system entirely if you don't have the correct data. The top left example there, a lot of the data that we see for vehicles, we see from the sort of the left-hand side where it's for self-driving vehicles. But if we're trying to look at car park flow and car park space availability, we need that top-down view. Likewise, the location one, if we've created all of our data, recorded our data in one location, we need to make sure that we can actually spread it across multiple different deployment areas. One solution to a lot of these issues is the use of synthetic data. So instead of using real world data, what we will do is we will create a virtual world and we will use the pixel perfect annotation from that. This has a lot of advantages, in fact, for us. It reduces the requirement on those real images, so that saves us time and money, and it can improve system accuracy. Now, I'm not going to go through this slide in detail. There's a lot of comparisons here for the real data versus the synthetic data. So later on, perhaps if you're interested, you can reread it. But basically, we need both of these. Both of these will help us build the trusted AI system by combining the real data and the synthetic data together can actually help build a system that is even more secure from the perspective of the data that is used. So just in conclusion, you have to be planning for data from the outset of your project. It's all too often we see, people out there who are creating AI systems for whom data is an afterthought. It needs to be thought of right at the outset because it really will make or break your project. And a lot of engineers that are out there spend significant amounts of their time trying to find that right data. It is a living thing. So, the data drift one, I think, showed that very well. But, data has a lifespan and some data will need to be introduced to your project. Also, you may need to retire old data. It can bias your system in ways that you don't actually want by having older data. The data diversity, again, really will push that, help you to get that non-biased system. And the use of synthetic data can help address any of the shortcomings that you may find in the real data sets. So with that, I'd like to thank you all for your time today, and please do feel free to contact me directly with any questions that you may have around data requirements.
Thank you, Chris. Mike here. So we've got a couple of minutes for questions. The one that I've got is how do you measure the quality of the data? Is there any metrics that you can use that will be needed for safety applications, for example?
It's very difficult, really. The measure of the quality of the data comes in the measures of the quality of your trained network. So it's the traditional measures in terms of the accuracy of your network, so intersect over union, traditional things like that will be the measures that you're using, and from that you'll then have to go around the cycle again and train the network with additional data and see how that has impacted your results.
Okay, and how would you detect data drift?
I think you detect it by seeing that over time your system is becoming less accurate. It is giving you more false positives, more false negatives, and if you see that over time that is changing, you would need to analyze, well, what has changed that is causing that. So that's really data drift is something where you'll detect the performance of the network getting worse over time.
Okay, thank you very much, and we're bang out of time, so that's perfect. Thank you very much, Chris.
Thank you.
Hi, Angela. So we move on to William.